Okay, so I'm starting back up. Question number 10. An engineer is going to redesign an ejection seat for an airplane. The seat was designed for pilots weighing between 150 pounds to 191 pounds. The new population of pilots has normally distributed weights with a mean of 159 pounds and a standard deviation of 33.1 pounds. If a pilot is randomly selected, find the probability that his weight is between 150 pounds and 191 pounds. Okay, to answer this question, I want to give you a couple visuals. So I've got a normal distribution that I've created here. It's scaled, as you can see. So it might look a little bit different than some of the ones that we're using with our calculators. And I want to take a snapshot of this. And I want to point out that because the mean here is 0 and the standard deviation is 1, this could be labeled with z's. So this is our standard normal distribution. And the standard normal distribution is unitless, so we can just apply a transition between a non-standard distribution to these z-scores. Then we go to the z-table, and that's essentially what this is doing. I'm actually using an integral function of this program that I have, and what it's doing is whatever endpoints I use here, I'm just using endpoints -2 to 1. It'll integrate underneath the curve, our density curve, right? It'll integrate it and it'll give me the amount of area that is calculated in that region. So, and remember that on the probability distributions, the total area is supposed to be 100 or 1. So that's why this is, it's taking up most of the curve, so it's turning out to be 8/10, close to 1. Okay, so in this case, I could maybe label this for visual with a bunch of z's, because there's really these unitless z-scores are really filling in this space, and they're not telling us anything. They're not specific to like IQ scores or to heights or to weights or whatever. Okay, then I could take that same distribution and I could change it. So I'm going to modify it for this problem. I'm going to modify it based off of the mean being 159 and the standard deviation being 33.1. So that's going to take a second, so let me do that. And I want you to see, as I make this change, what's happening. Now, first of all, you don't see the vertical axis anymore because I had it centered at the origin, and now the origin is further over here to the left. Or in other words, I've come all the way out here to 159 where the mean is. And you don't see the curve really anymore because the scaling changed the effect to our eyes, right? So I'm going to go ahead and draw back the horizontal scale, change the ratios here, and in addition to squeezing the x-axis together, I'm also going to stretch out the y-axis here. So I'll just keep stretching out this y-axis. Okay. And that's gonna make it look more like what we're used to, right? But you'll notice how the highest point on this is, it's coming in somewhere around here between 1/100th and 15 thousandths. So keep that in mind. Then the curve region going from -2 to 1, I'm going to change that because it doesn't make any sense to go from -2, so I'm going to bring that over. I'm also going to bring this over. So, and then now I can start fitting in this region of the curve, because if 159 is the mean and they're moving by standard deviations of 33.1, 33.1, 33.1 in the negative or in the positive, And we have those empirical rules and Chebyshev's theorem and other rules that tell us we typically expect to fit with 4 standard deviations across from the usual min to the usual max, but even if we're fitting more, like 3 standard deviations or 5, we're still not going to expect to be able to fill this whole region unless we really get over here. Okay, so let me adjust it just a little bit more, and now I can spread this area as far as I want. Let me take this back down to the picture too. So instead of this being a standard normal distribution, what we have here is a non-standard normal distribution. Still a normal distribution because we were told that it was, right? And so we're following this calculation, this density curve here. But instead of this being labeled by x and being unitless, labeled by z and being unitless, it's going to be labeled by x, and it will have units. And the units are whatever our x values are, and they are pounds. And so in here we've got a bunch of data, right? So we take all these men's weights that are normally distributed, and we get their weights, and someone has a weight of 80 pounds and someone else has a weight of 220 pounds, and someone's close to the mean has a weight of 160 pounds. But so it's just the data from the men's weights. Okay. Now we can find that, and that is the first question. If a pilot is randomly selected, so one pilot randomly selected, find the probability that his weight is between 150 and 191 pounds. And actually, I can do this dynamically, actually. It was 150, I think. Might be easier to just type in the number, but let's see if I can get really close. There's 153. Okay, then there we have the area underneath this normal distribution. It's not a standard normal distribution, it's non-standard. So these are x values in pounds, and it's from 150 pounds to 191 pounds. What's the probability that I could pick a pilot, a single person from this distribution? It would be 44%, basically, 44.03. Okay, and then they ask another question, and this is going to allow us to apply the central limit theorem. It says, if 33 different pilots are randomly selected, find the probability that their mean weight is between that same range. So what we're going to have to do here is we're going to have to consider this distribution as a distribution of, well, not this distribution, I'm sorry, we're going to have to modify it a little bit. But we're going to have to consider the distribution that isn't made up of just a bunch of data points of men's weights, but is made up of men's averages of men's weights of size 33, and n is size 33. So what we'll do is we'll just imagine every possibility where you could take 33 men, find out their average, plot it. 33 men, find out their average weight, plot it. Keep doing that over and over and over. Well, the central limit theorem says, and I'll take us to the sheet where it says it or summarizes it at least. It says, and I think we learned that in chapter 6, so since I'm using this chart, it says that the mean of the distribution of sample means, every time you take 33 men and find out their average weight and plot that and make a whole distribution out of it, is going to be equal to the expected population mean. And then, and this is if our sample is greater than 30, so we're not even concerned about that, even if the parent population wasn't normally distributed, which it already was, but we'd still apply this. And that their standard deviation is going to be equal to the population standard deviation divided by the square root of n being the sampling size that we took, and we took sample size of 33. So I'm going to make just one small adjustment then, and I've got to get this new skinnier population standard deviation by doing, let's see here, we had 33.1, The 33 number is pure coincidence. That just happens to be what the numbers turned out to be, divided by the square root of 33. So 33.1 divided by the square root of 33, and that's going to be 5.76 blah blah blah. So, you know, I'll try and get as close to that as I can. But that means now I can change, I'll get to the dynamic view. I can change this to, what was that again? 5.76 something. I'll make it more accurate, but you can see as I was doing that what was happening to the curve. This is a different distribution now, where the standard deviation is much skinnier. In fact, I'm going to adjust my view here, but I'm not actually changing the distribution. I'm just going to change my view. And I'm going to leave it a little tall and skinny. I have not changed my endpoints of 150 to 191. The range is staying the same, but I see that I'm already taking up way more area because everything got skinny, right? It pulled in on itself. And that's how the central limit theorem, that's how it works. Okay, so let me make a minor adjustment here to get more accuracy. So, okay. And let me take a snapshot of this, so that again we have the visual. No longer are these z-scores, no longer are these x-scores. These are now all a collection of samples, and we should remember that they're samples of size 33. So you take all the possible samples of size 33 of men's weights, you average those 33 people's weights, and you mark that down. Do it again, do it again, do it again. Create this entire sampling distribution. So these are a bunch of means, right? And they're creating this distribution where the mean of this equals the original population mean, and the standard deviation of this equals the population's standard deviation divided by square root of 33, square root of n. So that was our 33.1. This is our 159. That's why that didn't change where the center was. You notice the curve did not move over, but it did get skinnier because we basically pulled in, or we shortened the length of a standard deviation. So when you're using the same interval between 150 and 191, your area underneath the curve is going to increase. So let me try that, 94085. Actually, just to be sure, because there's a certain level of accuracy that this obtains, and I'm not sure if it's close enough, let me go to StatCrunch for both of these and remind you how to do that. So you can always open StatCrunch. And while it's opening, I'll just go ahead and grab that number. What was it? 9409? Okay, it looks like it's open. Okay, you can hit Stat. Remember how sometimes it does this fickle, it's kind of temperamental, and you have to click on some sort of cell. Okay, you go Stat, Calculator, and I'm going to choose a normal distribution where the mean is 159 and the standard deviation is 33.1. And then I'm going to choose between. Cool feature that's available on the calculator, has been on the calculator for a long time, but recently became available on StatCrunch. It's also on StatDisk. And unfortunately, Excel, you'd have to pre-program it, but you could kind of make this happen there too. From 150 to 191, this should be the first number we got, which that is rounded the same, 4403. Okay, and then let us change this from 33.1 to Now what's cool in the calculator is you can put in 33.1 and actually write divided by square root using the square root function. 33, because that was our sample size. Hit enter. You can't do it here, so sometimes one technology will beat the other one. I already have it calculated here, so let me just go ahead and copy that and paste it. Okay, now I'll hit compute. And there's our 94.09. So it was turning out the exact same as my dynamic sketch that I had right here. What's the final question? This is not, all that other stuff I talked to you about was just giving you the full understanding of the central limit theorem, well, as much as I really wanted to review. But then you got to put it together here. When you're actually designing an ejection seat, which probability is more relevant? And I would have to go with, because of the situation, we're not really concerned with the average weight of 33 people getting into the plane. We're concerned with one person getting in the plane and determining how many people are going to be able to fit that category of weight. Do we have to make an adjustment? Do we have to redesign this plane because people's body sizes have changed? Or are we good? And so I would say that the seat performance for a single pilot is more important. So the probability for part A would be more important, because that's the probability of a randomly selected pilot being able to fall in this category. And I don't know what their benchmark or their tolerance is. Maybe this isn't fitting enough pilots if it only fits the 44% of men's weights, the normal distribution of men's weights. But I think it's okay, because that's a very large number, and so I wouldn't redesign a plane. They cost millions to make anyway. Alright, so hopefully that helps you with that question. Let me see if I can get a few more done before I call this video off. A newspaper provided a snapshot illustrating poll results from 1910 professionals who interview job applicants. The illustration shows that 26% of them said the biggest interview turnoff is that the applicant did not make an effort to learn about the job or company. The margin of error was given as plus or minus 3 percentage points. What important feature of the poll was omitted? We've got options here: the sample size, the confidence level, the confidence interval, or the point estimate. Let's go back and see what they didn't tell us. Show that 26% of them, blah. So we've got the margin of error, and we can work backwards from that for a lot of information. This is a tough question in some sense. I'm not sure what they're expecting me to imply and not imply. I know that to have a confidence interval, if I know the error, the maximum margin of error, I would have already had to know the critical value. In order to know that, I would have had to know the confidence level, because I would have needed to know the level of significance. I would have also had to have known the sample size. But ultimately, the piece that I'm not going to know if I know the error is I'm not going to know the best point estimate, the middle where I add and subtract my error. I think I'll just take the biggest one here that kind of covers them all, the confidence interval. We don't even know the confidence interval, right? So I'll come back, I guess, and see if that was right or wrong, but that's what I would go with. Some good confidence. So there's some good concept questions here. Okay, the critical value is z sub alpha over 2. That corresponds to a significance level of 3%. Oh, find the critical value. Okay, now this is the positive one, right? So I can just go ahead and scroll right on down to the table. There are two ways I can look at this. Since I'm doing a standard normal distribution score, and I know that it's symmetric because it's a normal distribution type, I can go from 3% on the left, and that's what I'm looking at here is the left area on the negative side here. 3%, which is looks like it's closest right there to negative 1.88. And then just recognize that they weren't asking for the negative one, they were asking for the positive one, right? So I could just say 1.88. If I was using a calculator, say this is my calculator, I could use, actually, sorry, the feature was already up, inverse norm. Use inverse norm, say how much area I have to the left point. Oh, I'm sorry. In this case, I say how much area I have to the left, which is the complement of what I see. So it's going to be 1 minus 0.03 in half, because it's for a confidence interval. Oh, and that is not something I did there when I looked up on the score. I was too eager to look at the table, so I just went straight to that 1.88, but really I should have split that in half first, which would be 0.015. So it should have gone to 0.015 right there, which is negative 2.17. I'll show you. There's your hundredths place. And then I would make it positive because I'm actually looking for the positive one. .17. Let me get back to the calculator. It made me realize I had not split it in half. Alright, so if alpha's 3%, split that in half, that's 1.5%. Then that's supposed to be 1.5% to the right of this value because we're using the positive cutoff score. Do all that in inverse norm, and it'll give you the 2.17 that the table would have given you also. In StatCrunch, we click Stat, Calculator. We're still dealing with the normal distribution. Since we're doing with the z-score, we'll leave this as 0 and 1. We want this time to have on the top, to have cut off half of 3%. So what is the corresponding critical value? 2.17. So you put in the area and then you hit compute. And that's because I said I want it to be up here on the positive side. So I said greater than or equal. Okay, so those are those 3 questions. I could probably stop there. Let me check the time. Yep, that looks like about the right amount of time for this video, so I'm going to hit stop. See if we got them all right. Yeah, I'm going to have to read into this one. Let's see here. The confidence level. Why is that the only feature? I mean, certainly that was omitted, but they omitted a whole lot else. I'll let you think about that. Good concept question. I think I also saw that we had something here wrong. Oh, I did not put a decimal. I put in 0.9409, but I didn't put 0.9409. If that happens to you on the final, or if you go back and look in your gradebook for the midterm or any previous quizzes, let me know and I'll make that adjustment so that I can give you that point back. All right, thanks.